Hello, thank you for coming. My name is Vinay Shukla. I'm a principal product manager with AWS, focused on Amazon Redshift. Today, we'll talk about and share with you how you build data analytics stack at scale with Amazon Redshift. So I have a lot of material. I will go through it and try to give you all that information. So in context of the trends that we are seeing, a lot of companies are still on-prem. The migration to cloud is still in the early phases. And all these trends will motivate later on what we'll discuss. So the growth in data is exponential. These are sort of, everyone knows that, it's exponential along many dimensions. And people want more types of insights, more types of analytics from their data. In that context, let's look at some of the challenges when you're trying to do data analytics at scale. What are those challenges? And this is not a comprehensive list of all the challenges, but I've tried to highlight some important challenges that are there for doing analytics at scale. Double-clicking on data challenges, the volume, variety, and the speed at which data is coming at you is growing every day. And that leads to, like, how do you manage that data more effectively in a cost-effective fashion? What may have given you right performance and concurrency for a smaller volume may not scale as you scale up the volume in terms of data, the volume in terms of number of users, the volume in terms of analytics queries. So performance and concurrency at scale becomes even more challenging and increases the complexity. Another challenge is when you're doing everything at scale, there is not a single analytics service or tool that does all types of analytics. So then the question is, how do you handle multiple analytic needs? And again, in all the contexts, security and governance becomes more important because now you have more volumes of data, and any slip up there is even more costly. So while you do that, the cost and flexibility in managing your data analytics structure becomes very important. So you want the system to be easy to manage so that you're not wasting your time trying to manage the system, and ultimately that affects your time is very expensive, so that affects cost and flexibility. So let's look at each of these challenges in detail and how, with Amazon Redshift, you can address these challenges. So before we dive into these challenges, I want to motivate that discussion with Amazon Redshift architecture today. So today, the Redshift architecture is what's called an MPP architecture, where Redshift has a leader node, and the leader node is responsible for accepting connections from outside, compiling the query, and that's all it does. It also has a catalog of all the information, and it sends the job down to what's called compute nodes. And compute nodes have a slice of data, and they're responsible for executing the portion of query on their own and then sending the result back to the leader nodes. So effectively, you can think of compute nodes as the ones that are doing most of the computation. Leader node is responsible for coordination and communication back to the client. Also, when you're trying to load data into Redshift, the recommended way is that you load data parallelly, and each compute node can load data directly from S3, and that's why you get the parallelism of many compute nodes working in tandem, and you load data in a parallel fashion. So this is the current Redshift architecture, and there is also a part of Redshift that's almost serverless called Redshift Spectrum that allows you to query S3 should you have any query, and you don't have to set up Redshift Spectrum. If you already have a Redshift cluster and you want to query data in S3, Spectrum automatically attaches to your Redshift cluster, allows you to query, and if you don't query anymore, that fleet is taken away. So this is an ephemeral part of Redshift without you having to set up anything for Spectrum fleet. So with this architecture in mind, let's look at those challenges I outlined earlier and dive deeper in there. So the first challenge we'll look into is how do you handle with explosion in the data volume, variety, and velocity. So one way today you can handle that challenge is leave that data in S3. In Amazon S3, you already know the scale of Amazon S3 is really the biggest data lake in the world. It can handle any volume of data. Also, using this architecture allows you to eliminate data loading time, because a lot of time you have data coming in through things like IoT devices, Kinesis, and other way data is being born in S3 as well, not just landing from so many sources. So by directly querying data in S3, you can eliminate the data load time. Also, you can not just query the data in S3 with Redshift Spectrum. You can combine that data in S3 with the data you have in Redshift, so you can have a unified view of that data. You can join the data together. This is another way you can allow compute and storage to scale separately. And what do I mean by that? So some customers have a lot of data in S3, and then they have multiple Redshift clusters pointing to the same data in S3. And those multiple clusters can be for different workloads, for different teams within their company or organization. They can be of different size. They can shut it down when one of the clusters without affecting other clusters. So that way, many customers use it for segregating their compute and storage. And with this architecture, as I mentioned earlier with Redshift Spectrum, you're not responsible for managing that fleet. There is nothing for you to upgrade, et cetera. So that's the serverless part of Redshift that you benefit from. There is also querying in S3 with Redshift Spectrum. We support a wide variety of data format from many of the popular open data formats such as Parquet, ORC, Avro, JSON, et cetera. And this architecture also allows you to adjust your cost on a pay-as-you-go basis. Rather, it's on a per-query basis. When you run queries, the price is based on the amount of data that query is scanning. So that's the current way you can handle a lot of growth in data. Is there another way? Well, you may have seen, so today, if you look at Redshift architecture, there are two types of node type. One is dense compute family, and then the other is dense storage family. Dense compute is what's on the top in the middle section here is DC2 family, and that has a lot more vCPU per unit of storage. And then there is the dense storage family that has more storage capability per unit of vCPUs. So today you have these choices. But what we have seen is as data volumes are growing, the data that customers have in the data warehouse is often a fraction of the entire data they have. And there are many reasons for that, but a primary reason is the cost. Because if you add more data to your cluster, you may run out of your cluster's storage capacity sooner. And what we have seen is it leads to growth in what I call dark data. So not all data is being analyzed with Redshift, and there is a gap between the total amount of data and the data you have. And it's primarily because of cost reasons that people are not storing all that data. So if the data volume is growing and you want to grow that data in your Redshift clusters, the solutions you have today are you can add more nodes to your Redshift cluster and grow the data storage capacity. So that's an option, but it increases the cost. The other option is you can remove some of the older data that you don't need, but that also requires some effort on your part. The third option is you can unload the data from your Redshift cluster and put it in S3, and you pay the low price of S3, but you still have the ability to query that data from Amazon Redshift Spectrum. So these are the three options so far. But now on Tuesday, you may have heard in the keynote session, we announced a new node type, third generation node type called RA3. So with RA3, you have the ability to scale compute and storage independently. You pay for compute and storage separately based on the amount that you're using. With this, you can size your cluster essentially based on the on your compute needs. The storage price for this RA3, and I will show that detail in the next slide, is very similar to what you pay for S3. So if price was the only reason you're moving data from Redshift to S3, that reason is not there anymore. Now, you don't need to worry about, hey, whether my cluster is running out of capacity. Should I add more compute nodes? Should I increase my cost? You don't have to think about those trade-offs because Redshift will allow you to store as much data as you bring. So best of all, I think, is that this is automatic, meaning in the sense, if you have your Redshift jobs, BI, ETL jobs, you don't need to make any changes to those jobs to take advantage of RA3 nodes and these capabilities that we have launched. So each node of RA3, it has a very large high-speed cache. Most of the queries are served from the high-speed cache. And if there is a cache miss, there is a very high bandwidth networking between the RA3 node and managed storage. And in the cache miss scenario, Redshift will very quickly fetch data from the managed storage, and there is not really much of a performance difference between serving it from the cache versus getting the data from the managed storage. Looking at some more of details about the RA3 instances, today the RA3 instances are available in the 16XL size. With this, you can scale up to petabytes, actually 8 petabytes of compressed data, which equates to tens of petabytes of uncompressed data. The RA3 nodes on-demand price in US East is $13.04 per node per hour. And for storage, you pay 0.024 cents or $0.024 per GB per month. So it's a very similar price to what you pay for Amazon S3. We are also launching a smaller version of this node type in the next few months. So what do you get with RA3 if you already have a Redshift cluster? And next few slides, I'll talk about how does it compare to your current Redshift. Should you migrate to this instance? What can you expect? So this node type, when you compare it to the current dense storage type, or DS2, for price equivalent comparison based on the on-demand price of DS2, you will get up to 2x of performance and twice as much storage capacity for the same price. And compared to other data warehouses, still 3x of price performance. Each node of RA316XL has a quota of 64 terabyte per node in the managed storage. So let's look at some more details of RA3 node. So RA3 node is built upon the AWS Nitro system, which has its own hypervisor to improve how the operating system handles different virtual machines. It has its own chip to handle dedicated security. And if you look at the RA3 node type, each RA316XL node has 48 vCPUs, and RA3 clusters have a minimum of 2 nodes and a maximum of 128 nodes. At 128 nodes, the largest RA3 cluster will hold of 8 petabytes of compressed data, which equates to tens of petabytes of uncompressed data. And each node will have a memory of 384 gigs. So let's look at if you should consider migrating to this RA3 node. So if you have a dense storage cluster today, and if you have one of the larger data warehouse, more than 10 terabytes of data, then I think RA3 would be very interesting for your needs and performance. You will get better performance at the same cost with RA3. So if you have DS2 8XL, and let's say you have 4 nodes of DS2 8XL, for the similar price, you will choose in 2-to-1 node count ratio. So for every 2 nodes of DS2 8XL, you will replace that with 1 node of RA3 16XL. And this in 2-to-1 node ratio will be price equivalent, and I'm using the on-demand price for this comparison. So for the price equivalent comparison in 2-to-1 node count ratio, when you migrate over from DS2 8XL to RA3 16XL, you will get up to 2x of more performance and twice the storage capability. But this ratio that I suggested, 2-to-1, is not the only ratio. You can scale compute and storage differently. So you can migrate in, if you want to reduce your cost and make some trade-off in terms of having less performance, you can have less number of compute node. So you can migrate in 3-to-1 node count ratio, and that will lower your cost. So these are the additional trade-offs you can make. You can even migrate in 4-to-1 node count ratio, where you're focused mainly on reducing your costs. You will not, in that case, get performance benefit, but you're focused on performance, or you're focused on cost reduction with that ratio. So if you have a smaller DS2 cluster under 10 terabytes, RA3 16XL may not be cost effective. I would suggest that you wait for the RA3 4XL to come out in the next few months, and then you can consider using that to migrate off. What about if you have the dense compute storage? So if you have one of the smaller dense compute clusters, like under 5 or 10 terabyte, again, this might not be cost effective for you right now until we launch the 4XL slice, the smaller slice of it. But if you have one of the larger dense compute cluster, let's say DC2 8XL, there, similar to the DS2, where I suggested 2-to-1 node count ratio for price equivalent, for DC2, I would suggest 3-to-1 node count ratio. So for 3 nodes of DS2 8XL, you can choose 1 node of RA3 16XL, and you will get, for the same price comparison, 8x more storage. So the use case, or the reason why this would be interesting, would be like, let's say you have a dense compute cluster today, and you're using not all of your compute, but you're using most of your storage, and you're running out of storage capacity. Then this would be an interesting option for you to consider, because if you make the switch from your current cluster to RA3 16XL, you will have a lot more storage headroom. So let's take some concrete examples and see what happens when you try to take this ratio. So we had about a month of preview with RA3 before it was launched. So I'll talk about examples 2 and 3. And so an example with a customer 2, they had 15 nodes of DC2 8XL. And if you recall, compared to DC2, I recommended DC2 8XL, I recommended go down in 3-to-1 node count ratio for price equivalent migration. But again, that's not the only migration choice you have. You can have a different ratio if you want to trade off price performance. So in that example, compared to 15 nodes of DC2 8XL, the customer had 5 nodes of RA3 16XL. So what did they get in terms of that? They found that most of their queries were 1.25 times faster, but some queries were a little slower as well. And the reason for that is dense compute nodes, as I mentioned, have a very high vCPU compared to the amount of storage. So if you are a DC2 customer and you are pegged for compute, not so much for storage, in that case, RA3 might not be a good choice for you to migrate. You should stay with dense compute, and that gives you best price performance. But if you are using dense compute and you're not 100% maxed out on compute, and you're maxing out on storage size, then RA3 16XL is a good choice for you. Another example is customer 3 here. They compared 16 nodes of DS2 8XL to 8 nodes of RA3 16XL in 2-to-1 node count ratio. And based on that, they found is most of their queries and ETL were 1.3 times faster. And the reason why I skipped customer 1 example would be clear to you in a minute when I'll introduce to you the customer 1 here on stage, so they can talk about it better than I can talk about it. But before I go there, let's say you have this expectation of price performance when you migrate to RA3. The next question is, how do you migrate to RA3? What are the trade-offs? What are the best ways? So there are two choices to migrate to RA3. The first choice is what I would recommend and is the best choice. The other choice is not a better option. So the first choice to migrate is use the restore from snapshot. So let me double click on that. Each Redshift cluster has a backup that's automatically taken with the automatic snapshot, or you may have manual snapshots running that are running at your own schedule, taking the backup. You can take the most recent snapshot of your cluster, and using that most recent snapshot, you can go to the console or use the equivalent API or CLI and say, create me a new RA3 cluster using that snapshot in the desired and using the desired number of RA3 compute nodes that you want based on the price performance trade-off you're making. And in minutes, you will get a new RA3 cluster. Once you have the new RA3 cluster, it is in addition to your current cluster, whether it's DS2 or DC2 that you have. Your existing cluster is not disappeared yet. So once you get the new RA3 cluster, you can do some evaluations, do some sanity tests, see if it's behaving as you expect. If in case things are not expecting, you can discard that and go back to the cluster you have. Once you're satisfied with RA3, what you can do is remove the old cluster and modify, and then use the modify cluster command to rename the RA3 cluster back to your old cluster's name. And the reason why I'm recommending that, because they will have the same name. You don't have to make any changes to your JDBC or ODBC clients, connection string, et cetera. So that avoids you some headache in maintenance there. The other option, which I will not recommend, is classic resize. And classic resize changes your current cluster into the older cluster, or sorry, your current cluster into a new cluster type, in that case, RA3. So this option I will not recommend. I'm just listing it here as completeness. Please don't take this route unless you have a very specific good reason. So with that, I will introduce to you customer one.
Hi, everybody. My name is Jonathan. I'm a senior software engineer at Duolingo. And I want to give you a quick overview today of our experience using the new RA3 nodes with managed storage. We participated in the preview. But before I get to that, I want to give you a quick overview of how we ended up using Redshift at Duolingo. So for those of you who aren't familiar with Duolingo, our goal at Duolingo is to make high-quality learning, language learning education universally accessible. And the main way we do this is through the Duolingo app. And out of curiosity, are there any Duolingo users in the audience? All right, great to see. So we're actually now the most #1 downloaded education app worldwide, and we now have over 300 million users. And I think some of the reason we've been able to grow this big is because of how much we use data to drive a lot of our decision making. And the most common way we do this is through A/B tests. At any given time, we're probably running about 100 different A/B tests. But we also do a lot of ad hoc analysis. So things like digging into why users might be leaving the app, or where pain points are in the app, or even trying to diagnose why an app might be crashing, for example. And all of these things are really good use cases for us to really take advantage of the data that we use. But when we first started out at Duolingo, for the first several years, we used exclusively third-party analytics tools. And a lot of these tools did really well for a long time, but as we hired more data scientists and data engineers, we wanted to be able to kind of get more direct access to the data and perform kind of low-level queries on the raw data itself. And a lot of these tools didn't actually give us explicit access to the underlying data. So in about 2017, we decided to move to our own analytics infrastructure. And so what we did was we built our own ETL around Kinesis, and then piped data into Redshift. And while initially this transition was a bit challenging, we had to figure out how to pick all the right sort keys and dist keys and when to vacuum. We eventually got it, and I'm happy to say I think the Redshift team has actually done a lot of great work in automating a lot of these processes for you now, and the barrier to entry is now much lower. But we also had some organizational challenges. So for example, engineers at Duolingo were used to sending giant, arbitrary properties along with tracking events. And so in order to handle all this data, we actually initially stored all of the data in giant JSON blobs in Redshift, which meant we weren't really getting the advantage of the columnar storage. But after we kind of discovered all these things through spending some time iterating on our design, we eventually got really fast performance with Redshift. We're talking most of our analytics queries that we run against Redshift finish in under 10 seconds. So naturally, when we saw how fast Redshift was, we wanted to put all of our data in Redshift so we could query it. And now this is a graph of our data growth over time. And when we first moved to Redshift in 2016, we had about maybe 10 terabytes of data. So at that time, it was totally feasible for us to throw all of our data into Redshift and not worry about it. But naturally, our data has continued to grow. It's become a bit more challenging to follow that pattern. And why is our data growing? Well, I think it probably grows for a lot of the same reasons you might be seeing your data grow. So inherently, this is cumulative data. So over time, the data grows because we want to store all of our historical data in Redshift as well. But also, our number of users has been increasing over time, more users mean more data. Also, engineers tend to try to add more tracking and not go back and remove old tracking. So we generally tend to collect more data over time because of just adding more tracking. And our organization is also scaling up, and more engineers means even more tracking. So all of these effects compound to produce this effect where, since we actually moved to Redshift in 2016, we've been doubling the amount of data we ingest basically every year. So now we kind of have this decision to make. Do we want to keep trying to scale up our Redshift cluster to handle this doubling in data, or are we going to have to kind of move data out of Redshift because we don't want to increase our cost? So I initially, of course, was eager to support the idea that we wanted to double the size of our Redshift cluster every year. But when I proposed that to the CTO, I got shot down because the idea of doubling our costs every year was not super appealing. So what we instead ended up doing was we used Redshift Spectrum and moved a lot of our data out of Redshift and into Redshift Spectrum. So this disk utilization chart for our Redshift cluster actually looks like this for a whole couple of years before this. What it tended to be was that we would keep using Redshift and load more and more data, and then we'd get very close to 100%, and then we would, in a panic, move a bunch of data out into S3 and then start accessing it with Spectrum. And these processes tend to involve some manual work. We end up kind of exporting certain data, and then we have to kind of edit our views in order to make sure that the people using the database transparently access data in Spectrum. But ultimately, this provided a reasonable temporary solution to our problem. We were able to move data out into S3, and we could still access it in Redshift. But from my perspective, it was a lot of manual work to manage these migrations over time. But one thing we noticed with these data access patterns is that actually, if we look at the kinds of queries people are running against our Redshift cluster, almost all of them are on very recent data. So what I'm showing here is the kind of the dates being accessed by ad hoc queries. And when I say ad hoc queries, I don't mean our automated analyses for things like experiment reports or things like that. I really mean the kinds of queries of data scientists and engineers running, asking specific questions on Redshift and writing manual SQL. And we can see that basically everybody is just looking at data from the past couple weeks. And if you go past a year ago, then basically no one is touching that data. So we see is that we went to all this trouble to try and push as much data into Redshift as possible, but a lot of it actually isn't getting queried by anyone. And one other thing, too, is that this kind of shows the breakdown over time. One thing we also observed is that not all the data even recently was being touched. So for example, a lot of our tables are very wide. They have 500 to 1,000 columns, maybe. And we would see that most people were querying only a subset of those queries. So they would be asking for information like, what is the app version on a tracking event, or what's the user ID, or the timestamp. But they were rarely touching some of the less commonly used fields. And so what that meant is we actually have this hot-cold data pattern even within the most recently accessed data. So you can imagine when we had this problem of running out of space in Redshift that we constantly had to manage with a lot of manual labor, and we have this very clear hot-cold access pattern, we were really excited to hear about the new RA3 nodes with managed storage. So we participated in the preview, and we did one of these conversions that Vinay was just talking about. Our main cluster is 14 DS 2 8x large nodes. And so we spun up the cost equivalent number of RA3 nodes, that's 7. And we used that restore from checkpoint strategy that Vinay was talking about earlier. And then in order to evaluate how this would perform, we replicated a lot of the processes that we have on our main database on this new database. So we set up our ETL jobs to load data into the new RA3 database, and we set up a lot of our cron jobs that generate automated reports to also run on this new cluster. And just to make sure that it performed well for ad hoc queries as well, we took a log of all the queries that were run on our main Redshift database by hand, and then replayed those on our new cluster. And so this is illustrated in this somewhat confusing chart on the right. What this is showing, each one of those data points is a query that we replayed on both clusters. And on the x-axis, you can see how long that query took to run on our current DS2 cluster. And on the y-axis, you can see how long it took to run on our RA3 cluster. And I've drawn in the yellow line here, which is the y equals x line. So everything below the yellow line performed better on the RA3 cluster. So you'll note not every single query performed better. There were some that did actually go slower, presumably because they had to reach out to S3. But about 78% of queries did, in fact, run faster. And the median speedup we saw was about 2.1x. So they were running about, on average, in about half the time. So we were really excited to see that. We also measured the performance of the new database using a query benchmark that we use to track the performance of the database over time. This is one that we made up that has a lot of the standard queries we run in our analyses. And we saw actually that this one performed even better with a 2.3x improvement. And finally, one of the things that excited me the most was that we saw that our copy performance improved substantially. So we do ETL jobs about every 3 hours, and they can take a long time to complete because we're piping in a lot of data into Redshift. And so by having this big speed up, we should now be able to do more frequent loads and get the data updated in Redshift in a more timely fashion, which will make people excited to diagnose problems that are happening in kind of real time with our data. So we're very excited to see this, and I think we'll be converting over our production database now that everything's out of the preview. And don't tell any of my coworkers about this, and they'll think it was just me doing engineering magic to make it happen. All right, I'm going to hand it back to Vinay to talk more about scaling with Redshift.
Thanks, Jonathan.
So let's, the topic for this session is scaling data analytics. So we talked about the volume variety. Let's look at other challenges of growing or building analytics stack. So performance and concurrency is obviously a big challenge. You may have seen on Tuesday in the keynote, we announced a preview for what's called Aqua, which is Amazon's advanced query accelerator for Amazon Redshift. So Aqua is a hardware-accelerated cache. It has storage that is active with compute. So it has a large amount of cache that's on separate nodes from Redshift's compute node. Just like Spectrum is serverless, this is also serverless. You're not responsible for maintaining any Aqua fleet. You will not even see that. The behavior you will see is faster query, faster Redshift startup time, faster access pattern is what you will see. But under the covers, we will have a fleet of Aqua nodes that are purpose-built with AWS design hardware and processors. And these cache nodes will also have the ability to run compute. So operations like filtering, scanning, and compression and encryptions, and even aggregates will run on these nodes so that less data moves from these nodes back to the compute node because a lot of that computation happens on these nodes itself. And what we expect out of this is 10x performance compared to any other cloud data warehouse. And this is available as a preview today. You can go to our Redshift website and sign up for the preview. And this is only available with the RA3 nodes that we have launched. So that's one way we are handling the performance challenge. Let's look at concurrency challenges. So concurrency, and before I introduce concurrency challenges, I wanted to introduce scaling in 2 axes, horizontal and vertical scaling. So as an analogy, let's say you go to a movie on a Friday night whenever the new movie has come out and the movie is popular. There is only one ticket window open. The time you're standing in queue or line is your wait time. And once your turn is, you're at the ticket window, the time it takes for them to issue a ticket to you is your processing time. So in that, like having multiple ticket windows open simultaneously is what is called horizontal scaling, versus if the ticket window person becomes more efficient and issues ticket in less time than before, that's vertical scaling. So if you have need for vertical scaling, what's the answer? The answer is elastic resize. If you want to change your current cluster's performance, so a job, let's say you know, and actually this is a customer we have that gets a predictable ETL job every Wednesday, and they know that job is very complex, and they want to process it in half the time. So that Wednesday afternoon, every Wednesday, they double the size of their cluster, and then they reduce the size to normal, and they process their job quicker. So that's one way you can handle sort of like making your jobs run faster. The other types of concurrency challenge that I mentioned is eliminating the wait time. So the use case is, again, you don't know when the peak demand of concurrent users will show up. You normally size your cluster at a lower size. You're not provisioning your cluster for peak demand because you can reduce your cost. So in this example, the way this works is that you have your main Redshift cluster. You can enable this feature on a given queue basis. So Redshift has the concept of queues. You can enable it on a, let's say, BI or analytics queue you have. You indicate how many concurrency clusters you want. And let's say people start lining up. With the analogy that I was giving, let's say there is a line starts forming for the ticket window. Redshift will automatically open up additional ticket window analogy or the additional compute clusters in seconds. And queries will be drained to that cluster. And best of all, every time your main Redshift cluster is running for 24 hours, you get 1 hour free credit for this additional concurrency scaling clusters. And when I said it's 1 hour a day or 24 hours, it breaks down to actually 2.5 minutes every hour your main cluster is running. So you don't have to really run your cluster 24 hours to get the credit. You accumulate credit at an hourly basis. And these credits accumulate for up to a month. So for example, where is this useful? Let's say you didn't have any need for concurrency for the first 25 days of the month. You have it now, and you're running for 25 days. You have accumulated 25 hours of credit of concurrency scaling. And if in the last 5 days of the month, if these concurrency scaling needs arose and you have this configured, those credits will be used to serve that concurrent demand in queries. What happens if you go over the free hour? Then you pay on a per second basis the query is running. And you pay on per second on the on-demand rate of your main cluster. With this feature, we have seen Redshift improve its throughput, which is the measure of how many queries are being served in a given amount of time, 35 times over 2019. So with this, like you can see in this chart, as the number of users are increasing, the throughput is increasing linearly because Redshift is able to linearly scale with concurrency scaling. So now this is a way of handling the concurrency challenge that comes with scale. Let's look at some other challenge that come with scale. So the other challenge of scaling is, as I mentioned, there is not a single tool that does everything. There is not a single analytics service that solves all your problem. You will still need, besides Amazon Redshift, machine learning, because more and more customers want to do predictive analytics. You have data science team. So you have need for multiple types of analytics. And in that environment, the architecture that works best is putting a lot of that data that needs to be acted upon by multiple engines in S3 and still retain the ability to query it from Amazon Redshift through the Spectrum feature, or query it from Athena, or run your Spark job with EMR on it, or let your data science team access the same data through SageMaker or any other tool that you have. So this architecture allows you to sort of enable multiple tools that you will need to solve the entire range of your analytic problem. In that context, one feature of Redshift that we launched recently as GA is export Redshift data in Parquet format. So you may know that Parquet format has become a very popular open data format. It's based on Apache Parquet. And that Parquet format is supported by various services such as EMR, Athena, besides Redshift, Glue, and SageMaker. So with this format, you can think of Redshift as an ETL tool. You have the data in S3. You can bring that data in S3, do some transformation, or you have some gold copy of data that your data science team wants to run on. You can export some of that data in Parquet format, so the other engines who's accessing that will be more proficient because Parquet format compared to CSV is 6 times faster in terms of processing. So you can export the data out as Parquet, and now with the export of Parquet, it is even, we even support partitions. So when you export out, you can specify the partitions that Parquet has. So the data is written out in the folder structure of Parquet. So this is available that allows you to share your data across analytics engine to scale out. The other scaling challenge that we have seen is obviously with security. So oftentimes the first, and as an analogy, Redshift provides security at no extra cost to you. So if you already have a Redshift cluster, and let's say you want security unlike some other cloud data warehouses where security costs extra, we don't think security should cost extra. It should be just included with you, with your cluster. So Redshift not only has built-in security without extra cost, it is also integrated with AWS ecosystem. Like, for example, it is integrated with AWS IAM. So if you have identities defined in AWS IAM or federation that you have configured in AWS IAM, those identities can be used to log into Redshift or use Redshift. There is also in Redshift support for end-to-end encryption that includes both data in motion or data at rest. So we support for data in motion TLS or SSL. And we also support encryption at the disk level and the encryption keys are stored in AWS Key Management Service. Not only these integrations are there out of the box, there is also a wide range of certification for security and compliance, and the full list is there on this URL. So that's already an existing feature of Redshift. A new feature of Redshift that was announced a few months ago was column-level access control for Redshift, and this applies to data that sits in the data lake. So if you are using Redshift to query data through Spectrum, you can define. So let's take a scenario that for PII information, you may have a policy that says only a certain group of users should have access to certain PII-sensitive columns, and other users who are not in that privileged group should not have access to. An administrator can use the AWS Lake Formation, define that policy using the Lake Formation console or the API or CLI, and then when that user who belongs to a given group shows up and they are running that query through Redshift Spectrum or through Redshift, and Spectrum is under the covers being used to reach out to that data sitting in data lake. Depending on the policy the administrator has defined, they may or may not see certain columns as dictated by the policy. Best of all, the same policy that are defined by the admin is applicable across the other engines. So you can have a uniform policy that is enforced across Athena, Redshift, because it doesn't matter if you have policy defined a given group should have access to a given column. That is generally irrespective of the tool being used to access that. So this feature is there as GA since, I believe, September of this year. We are also working on similar feature for column-level access control for Redshift natively. That should be out in preview very soon. The other thing we have available is Azure Active Directory integration. So not to get confused, Redshift already has Active Directory support, and a lot of customers use that, and that Active Directory is on-premise. Now, Active Directory that is deployed in Azure, Redshift also has this available as a preview, and you can use this to configure Azure Active Directory. Now, let's look at other challenges you have, and especially challenges around cost and having flexibility. So one of the ways, and the reason why I am talking about this, is oftentimes you have data that's being born in OLTP systems like RDS or Aurora, where most recent data is being born, and you typically have an ETL job that moves some of that data to an analytic database or data warehouse like Redshift. And because you're running that ETL job, you're maintaining that ETL job, it comes as a cost to you. So now you can avoid that cost by having Redshift query the data directly in RDS or Aurora or other Postgres compliant data warehouses. So this allows you to combine your join and run a unified query across your operational data with your analytic data, and it can simplify your ETL pipelines. So this is available as a preview. The other preview that is now available is materialized views. So materialized views are used for complex calculations. So let's say you have a very complex calculation, and traditionally customers who are migrating from a legacy data warehouse would be interested in this feature because this simplifies your experience in terms of migration. It saves you the effort and cost of having to rewrite that in some other way. So now you can take advantage of this materialized views to more easily migrate from your existing legacy data warehouse. The materialized views are basically compute once, and if you have a query that is using very complex join, you don't want to pay that cost on every single instance, every single invocation of that query. Materialized view essentially are compute once, and you can query it multiple times. When the base table changes underneath, Redshift is able to incrementally refresh the materialized views. And for now, the maintenance of the materialized view in terms of how often is refreshed, it is user-triggered or user-controlled. So if you loaded a lot of data, you can call the refresh command and refresh your materialized view. Creation of materialized view is very simple, similar to how you create a view. You add a keyword materialize, and you create a materialized view over a complex query. So this makes migration to Redshift easier. The other focus for Redshift has been to make tuning and operations easier. And in that area, Redshift has made a lot of progress. So Redshift has automated the analyze task that you may remember if you ran Redshift a year ago. So analyze is basically a task that generates the statistics that are used by the compiler to optimize the query plan it generates. Essentially, it makes the queries run faster. So now this is not a maintenance task that you need to worry about. Redshift runs this automatically for you. Similarly, vacuum, think of it as a Roomba going around your house. Its vacuum job is also automated. When you delete some rows from your table, the tables are automatically compacted by Redshift. And if you add more data to the table, Redshift also now has automatic table sort. So if you keep on adding data to your tables, Redshift will automatically put them in the right sort order, and that speeds up your queries when they come. Redshift also introduced a new type of distribution style, disk style auto. So what it means is that if you have table created with a disk style auto, Redshift will automatically select the best distribution style for that table. When we create a new table, it will be set to disk style all. It will be there in every compute node. And when you add more data beyond a certain threshold, Redshift will, under the covers, if needed for better performance, can change the distribution style. So this is, again, automatic. This is just an FYI. You don't need to worry about that anymore. Similarly, for distribution key and sort key, Redshift Advisor generates recommendation. So based on Redshift Advisor, so some of you may not actually know that there is a feature of Redshift called Redshift Advisor. Imagine it's having a junior DBA just watching over your Redshift cluster and giving you advices. So that's a feature of Redshift that's been there for a while. So if you are not using it, I would say go to the Redshift console and look at the advice. So that advisor will also give you recommendation for distribution key or sort key if you have any that don't have. So this makes sort of maintaining Redshift cluster for peak performance much easier. And our goal is to make it fully managed and automatic, and we have made significant progress on that over the past year. Over the last month, we also launched a new Redshift console, and this makes managing your Redshift easier. The new Redshift console consolidates, if you have multiple Redshift cluster, it consolidates information from multiple cluster into one view. So you have, in a quick visual way, you can identify what's going on across multiple clusters. It also has good query monitoring, so you can drill down on a given query. Let's say a given query is running slow. You can look at how the CPU for your Redshift cluster was being used when the query was running slow. You can look at the visual explain plan or see how that query would have performed. And it also shows you recommendation in place, so you can see what you can do to rewrite that query or suggest to your user to rewrite that query that can be used to diagnose problems with queries, et cetera. There is also a built-in query editor. So we had query editor for over a year now. We have made it even easier to use. There is built-in visualization. You can also share the query editor with non-administrative user with a different URL now. There is command line assist and auto-completion, et cetera. There is Redshift also launched this year support for stored procedures. So again, this is similar to this stored procedure support makes migration to Redshift easier from your legacy data warehouses. So generally, if you are from a startup, you may not be using stored procedure, but anyone who's been using data warehouses for a decade or something like that, you know that stored procedures are very commonly used, and they are used for ETL, data validation, and custom business logic. So now Redshift supports stored procedures in PLPG SQL dialect. And best of all, there is a tool with AWS ecosystem called schema conversion tool, which you can point to your source data warehouse, and it will automatically convert the stored procedure of your legacy data warehouse, and it will give you an equivalent Redshift version of stored procedure you can copy and paste over to Redshift. And this makes migration to Redshift easier. It reduces basically your effort. Otherwise, you'll have to somehow understand that stored procedure first and rewrite that in some other way. So now you can avoid having to do that. Another cool feature of Redshift that was launched very recently is spatial query capability. So Redshift, so what is spatial query and where is it used? Well, we know that now location is there being tracked constantly by cell phones. It's being location-aware data is being generated by so many different devices, et cetera. So the need for analytics on location has become even more important now. So there, Redshift now supports a new data type called geometry that has further subtypes like points or polygons, et cetera. So now using that, you can run queries to figure out whether a point is within a polygon or not. Or, for example, the chart that you see on this, it shows the density of Airbnb in Berlin. So this allows you to do like heat map on a map. Right now, Redshift supports 2D, two-dimension spatial analytics. It does not yet support 3D dimensions. It also has 40+ functions, so you can write queries to figure out what is the distance between 2 points. To give you an example of what does a query looks like when you're doing spatial analytics, here is an example. You can see a query that has that's using the built-in data types and functions that Redshift now supports, and it's the same chart that you saw, the same map that you saw on the previous screen. It's just more zoomed in, so you can see each point is an Airbnb location in Berlin. So this is another way that you can see that Redshift has become easier to use. It now supports more capabilities that you didn't have before. And ultimately, it leads to you being able to do more, get to Redshift easier in a more easy fashion, and onboard or eliminate some of the other tools you may have used before. So this essentially reduces your cost and allows you to do more with your existing investments. So with that, let me try to summarize some of the benefits of Redshift. So Redshift is the only cloud data warehouse that follows the lakehouse architecture. What I mean by lakehouse, you probably are already aware of it, is you can combine your data lake and data warehouse together. and that's the architecture we see a lot of customers use. So Redshift enables you to use that architecture and store data for the lowest cost that you don't frequently access in your data warehouse, or rather in a data lake, and use your hotter data in your data warehouse. Redshift is also integrated with AWS ecosystem, so you can do queries like, you can take advantage of AWS integration with services like IAM, or Key Management Service, or CloudTrail, or CloudWatch, Lake Formation, et cetera. So you don't have to worry about these integrations. If you're using Redshift for multiple purposes, Redshift is already integrated with that. Redshift also has better performance than other cloud data warehouse. It's actually 3 times faster than any other cloud data warehouse. It's also 75% less expensive than other cloud data warehouse. And as we touched upon, the scaling Redshift for both data volume as well as in terms of users and in terms of making the queries faster, Redshift is more scalable than other cloud data warehouses. And it also allows you to scale storage and compute now independently with the RA3 instance we launched. Redshift is also the most secure without you paying extra for security. It allows you to run AWS-grade security with built-in integration with IAM, with built-in ability to encrypt data, both for data moving through the network and also data that's stored in the file system or a disk. It also has the most number of certification, and the full list was there on earlier slide. Redshift is also moving towards fully managed. We have made significant progress in that, like a lot of the maintenance and vacuum tasks have become automated. So that's all I wanted to give you a sense of the progress Redshift has made and summarize these benefits for you. So thank you for coming. And when you get a chance, if you can take the survey and give us feedback so we can improve for the next time, that'll be very good. And I won't have much time for the questions, but I will be available outside in the hallway. If you have any questions, we can discuss it there. Thank you.